Okay, so there's really not much more to say about two-dimensional motion. In two-dimensional motion, right, we solve two-dimensional motion problems by writing down our three equations in one dimension for each dimension. We might define them as x and y, or even three dimensions, right? X, Y, and Z. We don't come across three-dimensional problems very often. We do live in a three-dimensional world. I've said this before, but motion is mostly easily modeled in two-dimension, like cars on roads, cars driving in a plane, along a plane, right? Not in an airplane. Projectile motion, when you throw an object, it basically moves in a plane, in a two-dimensional plane. Now how do you get three-dimensional motion, right? If wind blows from the side and the projectile is blown off of its original trajectory, well, indeed, that is three-dimensional motion, but those are kind of hard to model, hard to write out, hard to put in problem form. So we're pretty much going to stick with two-dimensional motion, understanding that if we've got a third dimension, we can just add three more equations and four more variables. So there's not much more to learn about two-dimensional motion, but maybe I'll do one or two more examples. So let's just take the example of, let's say that you are in your second-story dorm window, and I'm trying to throw something up to you. Let's say that I am, or this is, let's give them names. This is George. George. And this is Ginny. Okay. It's always a bad idea to pick names that start with the same letter, so I can't subscript to them. But anyway, and let's say that Ginny is trying to throw something to George, and George, the window is 10 meters above the throwing, where Ginny is throwing from. And let's say Ginny is 5 meters away from the base of the building. Okay, let's start with that. Now, when you're throwing something to somebody and you want them to be able to catch it, especially when you're throwing up, what you want to do is you want to be able to try to throw it. There's a lot of speeds and angles that you could throw this object at in order to get it up to them. Let's say you're trying to throw them something. It's really interesting. I've seen this kind of thing where when they were building my house, and I really, really wanted a brick house. I grew up in a brick house, and I really wanted a brick house. So we decided to build a brick house. Brick houses are environmentally friendly also. So it was really quite amazing watching them. Once they start getting the bricks higher and higher, the bricklayers are up at the top, and the people at the bottom on the ground, Ginny on the ground, is throwing George bricks. And so it just takes a pile of bricks, and literally that's how they get them up there, is they just throw them up to them. And it's really neat to watch because they figure out how to throw them the most gently so that George can most easily catch them. So there's a lot of angles you could throw the bricks at. I mean, for example, if you threw the brick straight up, George will never catch it because it'll come down and it'll just land on your head. Okay, we don't want to do that. At what angle do you want to throw the brick? What if I aim directly at George and I throw the brick along that angle? What's going to happen? Well, remember, just with the monkey hunter experiment, right? It's got to fall, so it's going to do that. It's going to hit the building. It's not going to make it to George. Of course, you have a big target here, so if you're off a little, it's okay. You could throw it really hard and do that, and hit George really hard and make him fall backwards. And so really, there's a bunch of, we could throw it up and have it come down right through the window, right? So there's a lot of different initial velocities we could give the object that we're throwing George. What are we throwing George? Let's say that we're just throwing George a can of soda, right? George wants a can of soda. I've got the cooler down here at the ground, and I'm going to throw George a can of soda. George is, we're at college, and there's an outdoor party, but George is in quarantine. He can't leave. So Ginny is throwing George a soda. Of course, it's just a soda. So the question is what is the smallest speed So this is the issue with the bricklayers or with Ginny throwing George a soda. What's the lowest speed at which Ginny can throw George a soda in order for him to catch it? It's going to make it the easiest for him to catch it. And then, therefore, what is the angle? So, therefore, what is... So I'm actually asking, but what I'm really asking is what is the velocity that gives the smallest initial speed? What is the velocity that gives the smallest initial speed that Ginny can throw and George can still catch it? So before I even think about the concept of what it is I'm solving for, I'm just going to set up the problem. Let's set up the problem. Let's draw an x and y axis, right? Let's do all of our standard things. I'm going to draw an x and y axis, and I'm going to go ahead and say plus x is to the right and plus y up or down. Let's call it plus y up. We know the acceleration is down at 9.8 meters per second squared. That's the acceleration. We know the initial velocity is going to be, has got to be at some angle v0 like that, where the initial velocity, we can just go ahead and at the outset write the initial velocity in the x direction and the initial velocity in the y direction. And we don't know the angle because that's part of what we're going to ask. We're asking what is the lowest speed and therefore what angle would we have to throw it at in order to get it to George. So there's an unknown angle theta. I'm trying to draw that initial velocity v0x, v0y, v0x, v0y, and some unknown angle. What other things can we include in the picture? We've already got the distances, so indeed it does have to go delta x equals 5 meters in that direction, and indeed the soda has to go delta y equals 10 meters in the up direction. So those are the arrows for the displacement of the object, and and that's pretty much the picture. I'm going to go ahead and write down the equations of motion for the soda can. Delta x equals v0xt, delta y equals 1/2 ayt squared plus v0yt, vy equals v0y plus a sub yt, vy squared equals v0y squared plus 2a sub y delta y. Okay, those are our equations of motion. And then what do we know and what don't we know? Again, write it in a different color. You really, when you're solving these problems, you need to give yourself space on the page. I'm just trying to keep it on one page so that we can keep the picture in mind. Delta x is equal to plus 5 meters. Again, you've got to include the sign to show that you've thought about the direction. V0x is unknown, but it is in the positive direction, and looking at the triangle, it is V0 times the cosine of the unknown theta angle. That's unknown angle theta. That's V0x, right? We can just do the geometry of the right triangle just to write that out, because the speed is V0, the velocity is speed and angle, right? We got to give a speed and an angle. Well, or we could give the components. I guess I'm just going to write that out and see if we even need that. T is an unknown. We don't know that. Delta y is equal to positive 10 meters. Going through a sub y is equal to minus 9.8 meters per second squared because of the direction we chose as positive. And V0y is unknown, but it's positive because up is positive. V0 sine theta. Again, you might say, why am I writing that out? I don't know. I might need it. I might not. I'm writing it out just in case. And Vy final is currently unknown. Okay. So I just wrote it up there because I ran out of space, and conveniently our two unknowns are time and Vy final. Okay, so now I've written it out. Now we have to start solving. But now here's the question. What are we solving for? What are we solving for? Well, we want to know the speed, V0, and the velocity. Therefore, we want to know the angle at which we throw it. v0 and theta. But given what? Given what? Given that it's the lowest possible speed. So now you've got to think about what is going to be the low, what property of this problem is going to give us the lowest possible speed? The lowest possible speed that we throw it at is going to be, right, if I throw it too fast, but it still makes it into the window, well, yeah, then it's going to be still on its, if I throw it too fast and it makes it into the window, then it's still going to be on its way up. If I throw it too slow and it doesn't make it to the window, it's going to hit the wall. What I want to do is I want to throw it, the perfect speed to throw the object is the speed at which it stops on the way up, right? It's still got to reach George, but it stops on the way up. The perfect speed to throw it at is, in order to get the lowest speed, is going to be Vy equals 0. In other words, it's got to stop moving upwards when it hits George. That's going to be at the top of the trajectory. So the lowest speed I can throw it at and get it to George is if it reaches right at the top of the trajectory, right? We don't want the trajectory to be the top of the I can't say the word. I don't want the top of the trajectory to be below the window's level because it'll hit the wall. If the top of the trajectory is above the window's lowest level, then it's going to be going faster than it needs to be going. So that's the slowest. So what property do we know about the top of the trajectory? We know that when it reaches George, the top of the trajectory says that the vertical velocity is 0, Vy equals 0. So that's the additional information that we need to add given the conditions of the experiment. It's not really an experiment, but of the problem. Okay, now that being said, we can, so now we know more information, enough information so that we know that, okay, so we got to throw it at some initial velocity, V0, so that it makes it into the window like that. Okay, slowest possible speed is going to be such that, therefore, Vy final, when it reaches George, is 0. Again, a common error I have seen is just notice that the slowest possible speed is not the one at which you throw it so that the straight line reaches George, because this is projectile motion and the body will not reach George that way, right? Because it's going to slow down due to gravity. Okay, just moving on. So I think in the end, what we want to solve for is either V0x and V0y or V0 and theta. Both are going to give me the velocity, but now we've got enough information that it's just a plug-in to these equations with these conditions. So I've just rewritten the equations and the unknowns, and the knowns and unknowns, and now I'm just going to go through and say, okay, we know this, we don't know this, we don't know this, we know this, we know this, we don't know this, we don't know this. Well, there's really only two unknowns in that equation. We know this, we don't know this, we know this, and we don't know this. We have a lot of equations with two unknowns, so we could just solve them together. We know this, we don't know this, we know this, we know this. We can actually just use the fourth equation in order to solve for V0y. That's going to be the quickest, probably. And so I'm just going to go ahead and use the fourth equation and say Vy0 equals V0y squared plus 2 times minus 9.8 meters per second squared times delta y plus 10 meters. So therefore, V0y is equal to plus or minus 14 meters per second, and we're going to keep the positive one and say the negative one is not physical in this case because up is positive, we're throwing it up. Okay, 14 meters per second. So that's the initial velocity in the y direction, and we can go ahead now, and we need to find the initial velocity in the x direction. In order to do that, we need to know time, so I can plug v0y into either of the other two equations. Let's go ahead and do this one. That's going to be the easiest one. 0 is equal to plus 14 meters per second plus minus 9.8 meters per second squared times t. So therefore, t is equal to 14 meters per second over 9.8 meters per second squared, which equals 1.43 seconds. So now we can go ahead and plug into the first one and say, okay, delta x plus 5 meters is equal to v0x, we want to know that, times 1.43 seconds. So therefore, v0x is equal to positive 3.50 meters per second. So we're almost done. We're not quite done because now we have the x and y component, but I did ask for the minimum speed. I asked, therefore, what's the velocity, which, the velocity, v initial, is indeed plus 3.5 meters per second x plus 14 meters per second y. But what's the minimum speed? I guess I never asked for the angle because that's the velocity. The minimum speed, that's the minimum velocity. So the minimum speed, v0, the magnitude, is the square root of 3.5 squared plus 14 squared, which is equal to... So the speed is 14.4 meters per second, and that really answers the whole question. There's the velocity, there's the speed. But since I did talk about angle, we can go ahead and draw the right triangle. We can calculate for the velocity, writing the components. We can calculate the angle, 76 degrees. And so you could also say this is 76 degrees above the horizontal. Okay, towards the window above the horizontal. So that's the initial velocity. Here it is in component form at the bottom. Here it is in magnitude direction form. Done, done, and done.